Welcome to this video on moment of inertia part 4, finding the moment of inertia for other shapes. This is actually pretty fun because you can find a pattern and it kind of works all the way through. What we're going to do is catalog what we have so far, and then we'll see that that can actually help us shorten the procedure of doing the moment of inertia for other shapes. So starting off, we had axis of rotation at one end of the massless rod, remember the negligible mass rod with all the mass at one end, and we said that that was equal to ml squared, with L being the length of that rod. Now if we put mass on either end and the center of mass in the middle, we found that that was 1/2 ml squared. Then what we found was that if we spread that mass out over a continuous distribution and we found the moment of inertia about one end, we got 1/3 ml squared. And then finally, if we moved the axis of rotation like we did here, we moved that to the center, we got 1/12 ml squared. And so we showed as the mass was distributed closer to the axis that was rotated, or more of the mass was distributed closer, that the moment of inertia was falling, the resistance was less. Now the first thing we're going to look at here is a ring where all the mass is located at the edge of the rotating object. And again, it's rotating about the center here. So all the mass is located on the edge. So it's really just like this situation, except for instead of it being ml squared, because we usually refer to things that are circular in terms of r, we would have mr squared for a ring. Notice how if the dimension changes, if we now say instead of a ring, I'm going to do a cylindrical shell where all the mass is located at the very edge of this, it's going to change just a little bit because we have the mass, more mass possible, I guess you would say. So that's the change. But the equation is still going to be the same thing because it's all mass located at the same distance r. The mass along the height of this cylinder doesn't vary away from the axis of rotation. So the difference here could be that you have more mass, so the actual moment of inertia is more in the cylindrical case than this single little hoop. But the equation is the same. So that's pretty cool. I like that one. Okay, let's take a look now if we did a disk, because that might be a little bit different. So if we have a disk where it's not like this situation was just a hoop where we had mass all around the edge. Now the mass starts all the way at 0 in the middle and it's distributed all the way out until we hit the radius all the way through. So what I'm going to do here is use, again, my integral definition, r squared dm, like I used before in these cases, to find the moment of inertia. And I'm going to play around a little bit here to figure out what it would be. So now dm, remember, if this is uniformly dense, we have, remember this one, I'm not including any height. It's just a disk. So I'm going to say that its surface density is its mass divided by its area, which of course here is m over pi r squared, okay, because this is obviously a circular shape. Alright, so that would mean that the differential of every little sliver of mass is going to be equal to sigma times dA, and that would be equal to sigma times 2 pi r, that should be a little r, 2 pi r dr. Okay, so again, I'll change my variable of integration here from dm to dr by doing this, sigma 2 pi r dr. And you know, when you look at this, you know that you're going to be integrating from the center outwards, so from 0 to r. So let's do some simplifications here. So integrating from 0 to r, this is sigma times 2 pi times r cubed dr, and sigma and 2 pi are constant, so I'm going to integrate r cubed Okay, so that's going to give me 2 pi times r to the 4th over 4 from 0 to r, sigma times 2 pi times big R to the 4th over 4 minus 0. Okay, so at this point I'm going to go ahead and do just a little bit of simplification. So that would give me 1/2 out front here with the 2 and the 4, and then sigma times pi times r to the 4th. Now I know that sigma is equal to m over pi r squared, so I'll go ahead and substitute that in as well. So 1/2 times m times, or 1/2 times m over pi r squared times r to the 4th. Okay, and there's a pi at the top too. Okay, so r squared and r to the 4th factors, the pi's will factor, and there I'm left with 1/2 times m r squared. If you go through the examples, it looks just like this one. So just like this example looked like the beginning over here, this mass distributed evenly throughout, rotating about its center, matched with this. The only thing that changed is an L to an R. So that makes sense. Now if you think of this as a big solid cylinder, the same way that we went from the hoop to the cylindrical shell, it's exactly the same equation. You just might have more mass located at the end. The very last thing I want to talk about here is to show you a quick little shortcut that you can use if you're trying to just move the axis of rotation and you don't want to have to figure out the entire thing from the beginning. This is going to be called the parallel axis theorem, and the parallel axis theorem is really useful here. Because what it will allow you to do is just move your axis of rotation from what you did initially. And the equation basically says the new moment of inertia, so I'm going to label that as I sub nu, is equal to the moment of inertia that is about the center of mass plus m times d squared, m being the mass of the entire object, d being the distance from the original axis of rotation to the new axis. So distance from the original axis of rotation to the new axis of rotation. Okay, so let's just apply it to one of the ones we already looked at so we will know if we're wrong. We can check ourselves. So let's do the rod where we had, so we'll do the first example where we have the rod about the center. Okay, so our whole integration process got us to the equation that the moment of inertia equaled 1/12 ml squared. Okay, so that's this value, and it's the moment of inertia about the center of mass. So that would be the very center of this object, L over 2. Now what it's saying is if you want to shift your moment of inertia, so let's say I want to shift it to the end here. Okay, so the shift is going to go this way, and d is the distance from the original axis of rotation to the new axis of rotation. Okay, so d here will be equal to L over 2 because that's how far I'm shifting it. So what I'm going to do here is say that the new moment of inertia is going to be equal to 1/12 times ml squared plus m times the distance L over 2 squared. Okay, so let's do the simplification. So this becomes m times L squared over 4. So this is really ml squared over 12 plus ml squared over 4. So now if I do find a common denominator, let me move this down just a little bit. My common denominator will be 12. So that means I have to multiply this by 3 over 3. So I have 3 ml squared over 12. okay? And if I add those two together, I get 4ml squared over 12, and 4 over 12 is 1/3, so 1/3 ml squared. Let's see if that was what we had originally. So if I scroll back up here, I see, yep, it was 1/3 ml squared. So the parallel axis theorem allows me to make a quick adjustment without having to do all of the integration. You can do it with the disks and all of the other shapes too. So let's say instead of rotating it about its center of mass here, I want to rotate it about the edge over here. Well, I would be working with this extra piece here. So I have the moment of inertia about the center, and that was 1/2 mr squared. And then this extra piece here would be m times the distance, which is r squared, d squared. So that would be mr squared. So I'd have 1/2 mr squared plus mr squared. And you can see that you could figure out what it would be about one edge of the circle. So if the whole disk was rotating around this point on the edge. There's also a perpendicular axis theorem, which would flip the axis of rotation on its perpendicular side. We can take a look at that in a different video. I hope that helped.